DLSUD Dasmariñas inviting me for this webinar. So it's really good partnership, and also sharing whatever I know about the semiconductor industry. So let me share my screen now. Are you guys able to see my screen now?
Yes, sir.
Yes, sir.
Okay. Okay, let's start then. So, we're going to talk about IC fabrication, the trends, and we're going to talk briefly about Maxim and career opportunities. And then after that, we can have Q&A. So first, IC fabrication. So when we talk about IC fabrication, let's look at the big picture. It really is product research and development. So we start with ideas, then we look at, we define that idea into a more tangible product, and then we look at feasibility. Then we try to justify it so that we can have manufacturability, profitability. So all those financial metrics we really have to look into, and then we justify it, we develop, we send it to manufacturing, and then we launch it to the market. So that's kind of the big picture of research and development for any semiconductor industry. So as part of making sure that we develop a product on the right platform, on the right process technology, and the right package technology, we really need to look at what are available process, product, and package technology out there to enable us to provide the right product and the affordable product, and it's also marketable to our customers. And it's something that they also would want to use. So when we talk about wafer and process technology, really we look at how is the technology fit into a particular design. So when we started the semiconductor industry in the 70s, we started with 100 millimeter wafer. Unfortunately, that was, I wasn't working in the industry during that time yet, but I've seen those wafers. It's really is about 4-inch. And then in the 80s, we started with 6-inch wafer. So I have some of my products still running in 6-inch fab. And then we went to 8, then we went to 12, and now there's 18-inch. So the industry that I'm at, so if you look at the semiconductor industry, it really is dominated mostly with those digital companies, with those microcontrollers, microprocessors like Intel, used to be AMD, ARM. But there is some small players, which is really is the analog or mixed signal ICs, which is what Maxim is part of. So we have several peers, company peers that are into that, mixed signal IC, which is Maxim is one, Analog Devices, our neighbor, TI, onsemi, and more. So when the semiconductor started, it's 4-inch wafer. So if you imagine, if Intel was using this way back in the 70s, this would probably only have 1 or 2 microcontroller chips in there. So it's not really that, cost effective. But as soon as you increase the wafer size, that means that you can pack more devices in there. And as the wafer technology progresses, the process technology progresses as well. So they can pack in more transistors, and the transistors are even getting smaller. And that leads us to the next discussion, which is the process technology, or the process node, or simply node. Anyway, so if you have any questions, feel free to send your questions or interrupt me. So don't worry about it.
Mm-hmm.
So at this time, do you guys have any questions?
Any questions, guys?
So far, none, sir.
Okay, thank you. So when we talk about process technology or the node, it refers to the specific manufacturing process and its design rules. So with respect to how you lay out a transistor, how small you create these transistors. So theoretically, it's the gate length or the metal 1/2 pitch when we talk about, oh, by the way, the IC that I'm working on is in a 90 nanometer node. Or right now Intel is using or Samsung is using a 5 nanometer node. So when we talk about 5 nanometer, that's smaller than the coronavirus, I think. So when we do this, fabricate these wafers, we need to be in an ultra clean room to make sure that there's no particles like the coronavirus sticking into the wafer, because that could create into a particle defect later on. So as small as a virus size, that will already impact your 5 nanometer microcontroller circuit when, for some reason, if there's particle that's going to stick. So usually the leaders in the smallest process node are the digital domain. Because when it started, when the semiconductor industry started, it started with the digital circuit, and then the guys from Fairchild played around with it, and they converted the digital process technology and created an analog IC out of it. So those Fairchild guys, when they left Fairchild, those guys created Intel, created AMD. One guy who founded AMD left AMD and founded Maxim.
Okay.
So, I mean, if you guys are interested, you can read more about the Silicon Valley Genesis. There's some good documentation out there. So, this development happens in Silicon Valley, which is California, and also there are guys in Dallas as well who at the same time also developed a similar technology, and then in that area Texas Instrument was created and Dallas Semiconductor was created, and then eventually by the year 2000 Maxim Semiconductor bought Dallas Semiconductor. Anyway, so yeah, so if you look at the analog semiconductor industry, what usually happens is that the analog players like Maxim will buy old fab equipment. Like for example, if Intel is developing their 32 nanometer process node, which is the smallest distance that they can process, usually they will obsolete their old equipment like 90 nanometer machines or fab. So what usually happens is that those guys will sell it to the open market and the analog guys will buy it. Like for Maxim, we bought one of the 180 nanometer process fab way back early 2000, because the digital guys were tired of using it because they were developing like 65, 42 nanometer. And right now, 180 nanometer still is our workhorse. I would say about 80% of our products are still at 180 nanometer. And we just started this 90 nanometer technology. But for the digital guys, they already are in the 5 nanometer process technology. So the analog guys are really trailing behind the digital guys, but that's fine. I mean, that's how it is. And for analog application, we don't really need to pack that much smaller transistors and much density in there, because if you look at the analog world, we are more into precision analog, unlike the digital guys where they want to just pack in computing power in a small space. Anyway, so that's the process technology. So when when we selected what process node we're going to be using for a particular IC, then we start the design. So if you're going to be designing a microcontroller for Maxim, I mean, we have some low power microcontrollers. So we just started using TSMC's 45 nanometer. And I just had a discussion earlier that, about 25% of our product launches next fiscal year with some of our secure authenticator parts, it's going to be using 45 nanometer process, which is already kind of high tech for us. But really for the mainstream digital, it's not that high tech. Anyway, so once we know what process technology, we use the design rules, we use whatever guidance from the fab, from the process guys. Then we started creating this schematic, which is, IC design schematic. We can either use Cadence Virtuoso or Synopsys, but Maxim has chosen the Cadence Virtuoso.
Mm-hmm.
And then we do schematic entry, we do simulation, and that takes a very long time to do. But we really need to do it to minimize respin, because when we lay it out, we need to make sure that we guarantee that it's really going to work, because in a mistake, I mean, when we tape out and send it to the vendors to create this photo mask, or we create a mask set, it is kind of expensive. So we need to make sure that when we design, we simulate, and really have high confidence that whatever design we have really is going to be working. But there are cases that we want to take risk as well. So when we design in the circuit, we design in such that there's going to be redundancy that is built into the design. So we can put spare transistors, we can put spare resistors, spare comparators, whatever circuit that we want to do, we want to put in there. And we, collectively, or sometimes we call that option as CYA option. It's kind of a not so good sounding word, CYA design. It's cover your ass. Anyways, that's how we design it, such that if something breaks, we can easily tweak it. So the way to do it is put whatever plan A, plan B, plan C in there in your schematic, and then instead of, say for example, you found a bug, so instead of really changing all the mask set, which is pretty expensive, you can design it such that there's several masks on a part. So you can select a mask set that is metal mask, which is really the interconnect, which we can see later on, which is the interconnect between those devices on a planar IC process, and you can change the connection, and thus saving the full mask set. In the 90s, usually when we create those business models, we say that the cost to design, the cost to do the layout, the cost to do the simulation, the cost to do the full mask set, and the cost to fabricate the first set of wafers, that costs about $1 million on a 6-inch wafer process with a 1 micrometer process node technology. But nowadays, the cost went down a little bit because of some improvements. So it's in the range of about $250,000 to do that, design phase. So it's really costly to do this. That's why, to minimize the cost, there are programs called multi-project wafer, MPW. So those multi-project wafers, on a mask set, you can have multiple design in there. And TSMC allows that, and some other foundry allows that as well. So for Maxim, we're also using that for those unproven technologies. So if you're really doing R&D, which is really we're not sure, we're not confident, and we're using a multi-project wafer. Sometimes we call it the shuttle wafer, to minimize the cost of this mask set. So if there are more IC designers trying to design something that's kind of new, instead of spending $250,000 for a full mask set, then if there's 20 projects trying to do that same new technology, so you spend $250,000 mask set, but on 20 wafers, 20 designs, 20 different parts. So in a way, we can save money, and UP is also doing that, where they design in some circuit and they work with some foundries for a multi-project way to reduce the cost. Maybe DLSUD maybe in the future might want to try that as well. So anyway, so going back to our discussion, so if we are using a dedicated mask set, so each part will have its own mask set, and this is kind of the pattern. So on a mask set, it is more of a box, or sorry, it's more of a rectangle, and there's multiple die of the same device in there, and this is kind of one pattern. So this is used as a for photolithography process, and each photo mask corresponds to a layer for wafer processing, and we usually call it moves or steps depending on a wafer. So this is how it is being done. So this is the mask set. Hold on, let me. Anyway, so are you guys able to see my cursor, or is it too small?
Medyo small, sir, but nakikita po namin yung aninag.
Okay, let me try to change it.
Perhaps to a laser one.
Yeah. Sorry, I'm having issues with my setup here. Make it simple. Okay, and then to the settings. Are you still able to see my screen?
Yes, sir. Yes, sir.
Josh, are you able to see my screen?
Yes, sir. Yes, sir. Paki-hover po yung mouse. Try po natin. Tingnan.
Okay. Okay, now it changes. Okay.
Yes, sir. Medyo
Okay.
maliit lang yung laser, but it's, ano naman po,
Okay.
viewable.
Okay, thank you. So this is the photo mask, and this is the wafer. So as you can see, the photo mask is smaller than the wafer. So what's going to happen is that this is kind of the reticle. So reticle is defined as the tool that contains the pattern image and needs to be stepped and repeated in order to expose the entire wafer. So what's going to happen is each part of the wafer, it will be exposed by this photo mask, and it will be stepped. So it's not, the entire wafer is not going to be exposed at the same time. It's going to be done in steps. That's why it's called a stepper. So, so the wafer fabrication process is, there are several steps: thermal oxidation or deposition, masking, etching, doping, dielectric deposition and metallization. So when I said earlier about metal, this is the step where metal is deposited into the silicon wafer. And if you need to change your circuit because you found some problem with your design, then you can you can change the metal mask so that you can change the connection on your circuit. And then the last step would be passivation. So if you guys, since we really have a very limited time, I would recommend that you read more about this because this is really good. So you can refer to Modern Semiconductor Devices for Integrated Circuits by Channing Calvin Hu. So Mr. Channing or Mr. Hu used to be the TSMC CTO. So he used to be the Chief Technical Officer for TSMC, but he retired and devoted himself to the academe industry. I mean, to the academe. So moved from the industry to the academe, and he wrote this really good book. It's practical, but it's good for the academe. So if you wanna read more about this, I recommend that you read the book. And I found out that the PDF is also available freely in the internet. But I am able to
Nice.
I'm also able to order the book online. So Josh, let me know if you need the copy, the hard paper. I mean the paper bound copy. I have some.
Sure, sir. We let them know. We let the department know. This is a good
Yeah.
resource po. Thank you for suggesting.
Sure. Okay. So let's go to the next slide. So the next slide really. So what I summarized earlier was, we grow the field oxide. So our substrate, if we talk about silicon wafer, the substrate usually is a P-type substrate because in our circuit we ground the substrate. So to make sure that it's reverse bias, we dope it so that it's going to be a P-type substrate. And then the first step is we grow this oxide on the substrate. So there are multiple ways to grow it. To grow the oxide or the silicon dioxide, and the easiest way is to heat it up with a furnace about 3,000 degrees Celsius to oxidize the exposed area of the silicon wafer. And if you combine silicon and oxygen, it's going to be silicon dioxide, which is really an oxide. And then if you want to etch out that oxide because you want to create a FET transistor, so that's where the photolithography process comes in. So first you apply a photoresist on the top of the oxide after you grow the oxide. And then remember we talked about the mask set earlier. So we align the photomask, use one of the masks, and then we expose the mask set. I mean that mask and the wafer with the photoresist. So whatever that is exposed will be eaten up by the ultraviolet light. So that's what's going to happen. And then once that's done, we etch out the oxide because there's a photoresist. You only etch the oxide that is exposed. And then once you're done, we remove the photoresist, and that's the time where we have the part of the oxide that is removed from the wafer. And this is an iterative process. So so now we go back to this slide. So now you have a oxide that's removed. And next is when we want to create a PMOS transistor, we want to create an N-well. So to create an N-well, we diffuse the silicon with a dopant material to change the P-type into an N-type silicon. And to be able to do this diffusion, we again use the photo mask, photo etch, photoresist, so that we only diffuse this area here. So we have to go back to the similar process. So once we diffuse it, then this is now a a N-type semiconductor. Next is we want to etch this area here for the oxide so that we can create an NMOS. So again, we're going to go back to the same process to etch this out, and once it's been etched out, then we want to grow the gate oxide. So this is a gate oxide is the insulator between your gate and the transistor. So now you have the gate oxide that is ready for your. This is for your NMOS, and this is for your PMOS. And then we want to deposit a polysilicon, which is the conductor for your gate. So MOSFET is defined as metal oxide silicon field effect transistor, right? So when MOSFET was designed or developed, the gate element used to be metal, but because metal is hard to deposit and to maintain, they later replace it with a polysilicon. That's why, even though we call it MOSFET, but really, it's not really metal. It's polysilicon. But Intel was able to, use this 3D transistors now, which is beyond the scope of our discussion. So for 3D transistors, they're going back to metal gate. But for a typical CMOS process, planar process, not 3D process, we don't use metal gate anymore because the yields are horrible for those metal gate transistors. So we use polysilicon. And then we want to etch out the polysilicon because we just want to put it on the gate for your NMOS and PMOS. And then now we, implant the sources of your, this is your NMOS and this is your PMOS. So we implant, we dope it so to create a source and a drain. So this is your NMOS and this is your PMOS. And then we grow the nitride layer. And then we etch the nitride. We deposit the metal and we etch out the metal. So now, as you can see, we have this metal is your connection. So this is your NMOS, this is your PMOS, and then you connect, your NMOS to your PMOS. So this is the source, this is the drain, this is the drain, this is the source. You connect this to ground, you connect this to the supply, and then you can put a connection to your gate, and then this circuit really is an CMOS inverter. So are you guys able to follow me at this time?
Yes, sir.
Yes, sir.
Yes, sir.
It's loud and clear.
Yes, sir. Yes, sir.
Thank you. Thanks. So to simplify our discussion, so I only show a inverter, how to create an inverter using a CMOS process here. But for a typical IC, there's more into it. Like you need some transistor, resistor, capacitor, inductor.
Yes.
So,
Parasitics.
but it's a variant of this process. So, but if you really want to dig deeper into it, I would recommend you guys read that book that I mentioned earlier. It's good. Okay. So after that, this is what you'll get, a wafer. So I have some wafers here. Not sure if you're able to see this clearly. So this is are you guys able to see my video?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Wow.
Okay, thanks.
Pwede palang
So,
ilabas yan, sir, ah.
Ang laki.
andito ako sa office, Josh.
Nasa Maxim po kayo.
Sa Maxim. Kaya ako nakamask kasi we're, required to wear mask in the office.
I see. Nasa
Yeah.
office pala kayo, sir. Nice.
So this is the wafer. So as you can see, there's like a notch here. So this notch and this is the notch. This one is used for alignment. So when the wafer was created from ingot to create a wafer, it's being spun, and there's a notch, because this notch is not only an alignment, mechanical alignment, but it's also an alignment to the crystalline structure of the silicon. So everything has to be aligned so that you can dope it, and you can covalent bond the silicon with the dopant, right? So that you can align and dope the silicon. You need to have a reference for the silicon lattice structure. That's why there's a notch in here. And if you want to read more about it, it's also on the chapter 1 of that book that I mentioned. There's a good discussion in there. So anyways, this is the wafer. It's an engineering wafer, so I can touch it with my bare hand. But in production, we're not allowed to. Okay, so once we have the wafer, we need the wafer test for most of our products. And if you look at the wafer, it's really is very tiny. So we need to have an electrical contact on that tiny weeny die, individual dies. So what we do is we have a micro contact that will make good contact to the wafer. So this is really a precision machine design, and the cost for this is in the range of $10,000 US.
Wow.
Already like the price of a small car, brand new car, right? And I have it in my hand right now. So
For everyone's information, sir, DUT is a device under test, correct?
yes. Sorry. So yes. So wafer or DUT is device under test. So this is one of the probe card. We call it the probe card or the probe pins. So so this area here, it's this, and the pins that are at the center, I'm not allowed to touch it because I might break it. It's this one. So there's a very small pin, fine pitch pin in here.
Sir, a little bit higher lang po. Hindi po namin masyado makita sa screen. Yan! Awesome po.
Okay, thanks.
Nice.
So, yeah. So Josh, I haven't shown you this thing when you were here about a few years ago, right?
Yeah, I think I saw it. I still remember that, sir. That's a test board, tama ba?
Yeah, and it's a probe card. It's a vertical probe card. So this is the one that's going to be used to make contact with the die on a wafer, the individual dies on a wafer. So to be able to share to you a picture, I'm not allowed to share any information within Maxim, so I searched the internet and was able to find this. It's almost the same, so that I can give you some public information. So, and I can share you my slides after our seminar.
You flex. Oh. You flex to play.
This one is actually a UF 2000 prober, Josh.
Okay.
So it's actually the handler.
I mean tester.
Yeah. So I'll show you the tester on the next slide. So this is where you have your hardware through your tester. This is where we put the wafers. So this is how it looks like. So this is the wafer, and it's on a chuck. So there's a vacuum that makes sure that the wafer is in place of the chuck. And this is kind of the robotic arm that holds the wafer and put it in this location. And then the probe card is on this side. So let's look at the next slide. So this is the next slide. So this is the teradyne tester, Josh, and this is the prober. So again, I took this picture from the internet so that I can share it with you guys. So this is not a Maxim picture, so it's not confidential.
Yeah.
So so this is the setup of a teradyne automated test equipment, or we call it ATE, docked on a UF 2000 prober. So the test development engineers are the ones responsible designing the hardware and software to be used on the ATE or on the automated test equipment to test a specific wafer. So if the wafer is changing, if the product is changing, there's a big chance that your hardware is going to be different and your software is going to be different as well. We do this test development here as well in the Philippines. Okay, so that's the wafer sort setup, probe setup. So this is the picture of a die, and this square metal with some puncture in there are the metal pads or the band pads. So as you can see, there's already a puncture because it's been probed. So we really need to puncture this metal because sometimes this aluminum pad has been oxidized. So to make good electrical contact, we have to go through that oxidized aluminum and make good electrical contact. So the pins that I was showing earlier, this one, it will scratch the aluminum pad of the die so that it will have electrical contact. And then after that, there is a band diagram that we need assembly, and this is where the pads, and we tell assembly that this is how we connect through a band wire to the external pins. So we send this to assembly. Some ICs don't actually use band wires. So there's package technology that don't use band wires, but it's similar. It's an interconnect. So still we use it. We use this diagram, and we still call it band diagram. And then this is the package part. This is a sample QFN. And as you can see, there's again marks in here, and this means that the device has been tested. So now it's tested through final test. So now let's look at final test. So final test, we need to test the ICs. So there's multiple ways to test the IC. First is manual testing. So we can do manual testing, but we don't use that for production because it's too slow. So manual test is useful for initial validation of the IC by the IC designers test development engineers, application engineers. And then, there are cases that we get customer returns. And if there's customer returns, then it's something that the customer tried to use the IC and it doesn't work, so they return it to Maxim, and we test it again on the bench. And that's actually part of the failure analysis process. So in production, we don't use manual tests. So what we do is this automated test equipment. Again, it's the same tester that was used on the probe, but now instead of testing wafers, we test the ICs. But there are also packages that are wafer level. So even though we call it final test, but since the package technology is wafer level technology, so we still use probe. And that's applicable for CSP chip scale packages or wafer level packages. So this is kind of how it works. So you have your device under test, you have your socket pins, you have your flex circuit, you have your capacitor, flex circuit PCB, and then you have your adapter PCB, and this is where it connects to your load board. That's how a typical final test setup looks like. Anyway, so since we don't have time, so this is the end of the IC fabrication process. Do you have any questions at this time?
Guys, questions?
No.
Any questions, guys?
Sir, question po.
Yes.
Curious lang po ako on how semiconductor companies are coping up with the challenges po. For example po, kasi po 'di ba yung sa Moore's Law, ang challenge po is increase yung number ng transistors in a small wafer. So I'm just curious po kung paano po nagko-cope up yung mga kumpanya.
Yeah, that's a good question. So let me go back to the slides. So testing wafer is really challenging because with Moore's law, we have to pack in more transistors, and the pitch. When we say pitch, show you the pitch in here. When we talk about pitch, so the pitch is the distance between the smallest distance between the pads, and as Moore's law gets realized, we packed in more transistors, so there's going to be more pins, and the pads are getting smaller. So this pad opening for a 90 nanometer process are getting smaller, and it's way smaller even for the 5 nanometer process. So with that challenge, we have our vendors that are doing research as well. So what they have been doing is they are fabricating these needles using MEMS technology. And this MEMS technology is it's like processing a wafer, but they carve it out, they process it out, and it's a micro pin. And so far, we're able to successfully use this on our 90 nanometer process nodes without any issues. And that's why we're paying a lot of money to use this technology, because the vendors are doing research and we're paying for their proprietary research on those probing technology. And we have a roadmap, and when we tell the vendor, hey, in the next 3 years or 5 years, I will have a 20 nanometer process, and the pad size and the pitch is this much. Make sure that you start your research now, so that in 5 years, I can buy the probe card from you. So that's how it is happening right now. We work with our partners.
Okay, sir. Thank you po.
Sure. Yeah.
Any other questions, guys?
Yeah.
One question is from Jean Carlo de la Rosa. Would it be possible for a student hobbyist to design and especially fabricate an IC? Everything seems to be complicated and expensive.
For a hobbyist like me, I'm also a hobbyist. It's better that we design it in, I would say, system or circuit level, not on a transistor level. Yeah, because designing on IC level is very expensive. But if you're really into research, you can partner with the university to go into those. I mentioned earlier a multi-project wafer (MPW), and with multi-project wafer, we can have more products on a specific mask set. So the cost is distributed to each of those mask set. And if you're really into it, you can search multi-project wafer foundry. There are foundry out there that are willing to work with university or even with individual to fabricate some die for you. So if you work with those vendors, what you'll get are singulated dies. They won't give you the whole wafer because it contains die or products or design from someone else as well. So what they'll give you are the singulated dies, teeny-weeny die. And you'll have to figure out how to connect that die to a external circuit, which is doable if you have a probe station, which unfortunately I haven't shown here. So it's doable, but yes, I agree it's expensive.
Well, thank you for the question, Jing. Any other questions, guys? Let me steer the questions naman to something that is career related. So far, I think we have a couple of alumni working for Maxim in test under your department, Sir Norman, right? TSDA. We have, I think, Kim Guevara, Hexina, we have DK, we have GAP, Grace and Aligada, working in Maxim. Can you describe for us what's the typical job responsibility of a test development engineer, or at least someone in your department?
Yeah, so let me go back to the earlier slide here, because we are part of the research and development. So early on, we are involved in each of these steps. So when the ideas came out, we have to look at that idea if that's even feasible to be able to be manufactured. So we work with our partners in the US or in Europe. So when an idea goes out, so we look at what that idea is, what's the definition of that idea, and then we work with them on the feasibility phase and on the justification phase. So when a new idea goes out, usually it ended up as a design for an IC. And we will say, okay, I'm going to create an IC that is, for example, let's look at it as a op-amp. I think Hex is working with op-amps right now. So say op-amp, okay. So then the product definition engineer would say, okay, I want someone to design in an op-amp that has 100 nanovolts of offset leakage. So Hex will see that, and Hex will think, oh, how can we guarantee that the offset voltage of an op-amp to be 100 nanovolts. Then Hex is going to do some research to figure out how he can measure 100 nanovolt on a noisy environment. And that's the challenge. That is the challenge that we want to see. So there are many ways how to, fix that or find a solution to that problem statement. And Hex will work on that. He will work with the IEC designer to design in some built-in self-test or design for test or design for manufacturability, so that we're going to be able to successfully manufacture that 100 nanovolt offset op-amp. And then when that design gets started, then Hex is going to design in the hardware, is going to work with design how to test and implement that 100 nanovolt offset test in production. So what Hex is going to do is going to design in a board level design, so to interface from the wafer or from the package part to the automated test equipment. And then she's going to do a software as well, because there are power supplies on your automated test equipment. There are power supplies, oscilloscopes, signal generators, voltmeter, ammeter. So you have to command, send an instruction to all those equipments so that you're able to test the device under test or the wafer.
So it seems really fundamental skills that are needed for such a job are heavy foundational theories on circuit analysis, and for test development, right? Most of the test development area then, depende kung saan sila mapupunta, do codings, right, sir?
Yeah, we really emphasize more on the circuit analysis rather than the coding. The coding is pretty simple. I mean, we have one tester that uses Visual Basic, so I mean, you don't need to learn Visual Basic, right? I mean, it's too basic. But most of our testers uses C++, but it's so basic that you don't need to be an expert or be an IT guy to develop this software. Really, it's more of the electronics part of it.
I see. I think another interesting question coming from them, medyo shy na ata sila, would be what, sir, medyo ano na to, just give us a figure or a hint lang, would be, I think, what would be a starting compensation of an entry-level engineer in Maxim?
I would try to answer that because we have survey data. So we're actually working with the industry here in the Philippines to make sure that our compensation is competitive. So we look at Radford data, and we make sure that we are at the right compensation range. So we review our compensation every year. So our compensation is really competitive with respect to the market, and we try to compare it with IT, with anyone that we're competing with, because ECE graduates goes to IT, ECE graduates to another industry. So we want to make sure that we don't lose to those industries that are competing in the same pool. So we use those companies, Radford company, to get the survey, and they provide us the survey. So they're going to give us, okay, this is the distribution for the entry-level engineers. So Maxim is okay. We'll select this beyond the 60th percentile of the distribution so that we attract talents. So right now we're about I don't have the data here, but I think it's 20 something, close to 30K per month. So 20,
wow.
20 something, 27.
So wow.
That's it.
It's pretty competitive for a provincial rate.
It is, and really for Maxim. So I mean, we get the employee to own their development. So really, It's up to the employee to really, get all the opportunities provided by the company. And we have a very black and white structured career ladder. So if you move to the next level, I mean, the compensation goes up as well. Responsibilities compensation goes up. And yeah, so here we have successful engineers that works for us. I mean, people would start thinking, okay, when will they get 6-digit, salary, right? So we've been seeing people that are really successful under maybe 6, 7, maybe 7 to 8 year. They'll get into the
Wow.
to that range.
Another good thing in Maxim is that, for the information of my students, I'm not sure if I have already shared this. I interned, I had actually immersed in Maxim for a partnership program with the DLSUD. And the one thing I noticed to Maxim is that they have many, what do you call this, organizations and or events. For example, Toastmaster. It's a good, which usually you have to pay monthly to be able to join, but I think Maxim gives it away for free. Toastmaster is just one of the many, shall we say, organizations or activities that are available. So hindi ka lang, you're not just confined in your cubicle, but they really do offer a lot of things in the company.
Yeah, that's right.
I think we have another question. Chelsea, please go ahead.
Hello po, sir. I'm gonna ask if are there some kind of trainings or certifications po if ever we want to expand our skills and knowledge in microelectronics track? Kasi po parang limited lang po yung available na nakikita ko if ever. Thank you, sir.
Yeah. You mean once you are working at Maxim?
Yes, sir. Or if ever po we want to add it to our credentials.
As an employee, as a Maxim employee?
Yes, sir. Or
I think what she's trying to ask, sir, is she's comparing from other fields, for example, sa ICT, where they have CCNA certifications and other certifications. For the semiconductor industry in general, or perhaps for Maxim specifically, what do you usually offer in terms of trainings and certifications?
Yeah, so we have a lot of trainings. So not just Maxim. So for Maxim, we have a Maxim University in our system. We call it Maxim University. It's an online course that you can select all those online courses in there, and then no one is going to stop you if you want to select those. No one will stop you from taking that. And sometimes it's not for free, but if it's in there, the employee can take it at any time. And then we also offer the educational assistance program. If the employee wants to take master's or PhD, we provide the tuition for free as long as it's electronics. We cover that. And within Maxim, we have we have all the experts. You can ask any questions to them, and they will find time to answer you. So there's multiple way. Get a formal education, get through the Maxim University, talk and learn from the experts, and also Maxim has a good, I would say, chief technology officer organization where we have unlimited access to all IEEE deep dive, and we even have like partner universities in the US that provides seminars, webinars like this one. Usually I join those, but it's kind of hard for our time because it's kind of midnight or early morning our time. But they usually recorded those, and it's into our Microsoft Office stream page, so we can watch those training videos, and we can ask questions anytime if we just send email to them. So there's a lot of ways to learn at Maxim. So as soon as you start here, you never stop learning. That's what I can say, because even though I'm already 20 plus years here in the company, I still learn a lot of things. And I still read books, download IEEE papers for free within Maxim. So anything, I mean, you can learn here, Maxim.
Thank you, sir.
Sure, thanks.
All right. Any other question, guys? May gusto pa kayong i-raise na question. It's not every day that you get to ask a question to a director in Maxim. So I do encourage you to seize the moment and ask questions. Guys? Sige, ako magtatanong. Sir, I think siguro this would be our last question. Most of the students, of course, get their feedbacks from their seniors na alumni and graduates na. They ask them usually, kamusta, how's work, kamusta yung environment, etc., etc. And they have this, I think, idea that the semiconductor industry is a stressful industry. Can you comment on that? And how can we encourage students to consider taking a career in the semiconductor industry?
Well, I would say semiconductor industry is a challenging industry where you will really have to use your brain, you really have to think, but you will learn a lot of things. So if you're into challenges, if you want to learn every day, if you want to be better, if you want to have a successful career, the semiconductor industry is the right industry for you. There's stress, but it's how you handle stress.
Right.
And right now, when I started, Maxim was a little bit, young, and that was pretty stressful during that time because we don't have the tools and and everyone is an engineer running the company. So engineers, right? They want to get things done. We want to get things done, and we want to do what's right. And sometimes, there's really not much of a people focus approach. But things evolve. Things change for the better. So we have tools. We have good tools right now, like project management, where before, when we look at the stress distribution, so we're engineers, right? We look at graphs, we look at numbers.
Yeah.
Without the project management tools or any tools, if you look at the stress distribution over time, like if you plot it like time over stress, before, stress is going to peak out and it's going to go down, it's going to peak out, it's going to go down. So it drives us nuts. But now with focus on human resource and all those productivity tools, we can limit the stress. Instead of it's going to go up, what we can do is we use all the tools we have so that we can limit the stress and distribute it over time. And that is how we deal with stress so that people don't get burned out. So that's how we handle it. So we minimize the stress, we distribute it over time, we make sure that we get support from anyone who can provide support to really make sure that we don't burn out our employee or we don't burn out ourselves. So yeah, that's kind of how the semiconductor industry works.
Right. And it has been thriving. Well, for instance, Sir Norman stayed in Maxim for 20 years. There must be something that made him stay there. And yeah, it's for our graduates to explore. So please do consider the semiconductor industry and even Maxim. I believe with the current pandemic, the process for application and or hiring is on freeze. Tama ba, sir?
Kind of, but in the next few minutes, or maybe in 30 minutes, or maybe an hour, I have to interview someone in Thailand. So we're still interviewing. We're just following physical distancing. So we're using Teams, we're using Skype to do interviews. Yeah, so I think the only thing that's stopping us right now is the onboarding process. But that's kind of been a challenge, but we're still looking at candidates right now. Yeah.
Well, thank you very much, sir, for accommodating us for giving us your precious time. Salamat, sir. We extended a little bit. It's already 2:09 on the clock. But salamat po for giving us your precious time and effort in making this webinar possible. Guys, please say thank you to Sir Norman.
Thank you, sir.
Thank you.
Thank you po, sir.
Thank you, sir.
Thank you.
You're welcome. You're welcome. So Josh, I'll send this slide because there are some slides that we haven't discussed, but I know you guys are busy, so I'm just gonna send this slide to you, Josh, so that you
Yes,
can
sir.
Okay.
Sige po.
Okay.
All right. So with that, thank you very much, Sir Norman Fuentes, for Director, TSDA Maxim Integrated. Hope to see you soon, sir. Salamat po for spending your time with us. Thank you and God bless.
Yeah.
Bye, sir.
Stay safe, everyone. Thank you.
Bye.
Bye.